Underminer Studios, and we're going to have a lot of fun today. We're going to kind of go through this. I have about 25 minutes, so everybody rock, run, and ready to go?
Yes.
Cool. All right. So I am CTO and founder of Underminer Studios and Volumation. Volumation is our company that does volumetric capture and processing. I've been 10 years. I was in the entertainment industry. I started out as a technical artist, and I was in games. And then I moved on to movies, and now owning our own studio, we do a lot of visualization technology. So we do a lot of work in VR, AR, MR, everything in between. And one thing that's really interesting is 50 credits. I keep forgetting about that. So you spend enough years in the industry, you know, you start working on lots of different projects, and being that, you know, I spent so many years as a technical artist, I would go from a bunch of different projects. So I would be doing automation on one game, cleanup on another one. So it was something that obviously I really enjoyed. So let's move on. So what is volumetric capture? Obviously, it's the attempt to humanize the digital world. Volumetric capture and photogrammetry bridge the gap between the real world and the virtual world through the use of advanced computer vision, machine learning, mathematics. It allows realistic environments, objects, and people so that we can engage and immerse ourselves in the digital world. So how many people have seen really bad mocap? I mean, take a look at some of the last movies that have come out. We start digitally aging people, bringing them back to younger versions. And one of the big things that people are really starting to get into is not only facial mocap, body mocap, and one of the big things that you end up getting is, you know, we're starting to really run into that uncanny valley. The uncanny valley, for anybody who doesn't know, is as things become more realistic, at a certain point, people realize that this isn't something that's real. So we go ahead and we look at it and we go, whoa, this is, it's disturbing. It's not really human, it's not really not human, and then it starts perturbing us. And so it starts falling into that lovely trough. The really cool thing about volumetric capture is, since we're actually live capturing people, the thing that we do is we jump right past the uncanny valley, and then we end up getting things that look extremely realistic. So what are we going to cover today? Obviously, photogrammetry and videogrammetry, volumetric capture just in general, and AR, VR, and MR. So it's going to be a lot of information, a lot of really cool things that we're going to cover here today, and we're going to have a lot of fun. Photogrammetry in general. So to understand volumetric capture and processing, you'll end up needing to understand what is photogrammetry. This is the basis of technology, which is actually really kind of cool. The technology itself, or the ideas and the concepts that we have, goes all the way back to like the 1800s. The first patent that we have is like 1917 for something that we could actually consider really photogrammetry, being able to take multiple images and then go ahead and get their distance. So it's the science of taking measurements from photographs. And through that technology, we actually get really cool three-dimensional meshes. So how does it work? Obviously, you have a whole bunch of cameras. It's a giant array most of the time. Take all these different photos, and then we go ahead and use detection points. If anybody is familiar with OpenCV or any other system that goes through and understands different interest points that are in cameras, it goes through and it goes, oh, this is interesting. And it looks at another photo and goes, hey, that's interesting there too. Oh, in between the two of these, I understand that this is probably 5 feet away, and then according to the other one, it's about 5 feet away too. And so it ends up building a mathematical model out of all of the different photos that you've created over and over and over again. As you can see, it says repeat thousands of times, which it does. Some of the different systems go through and repeat, and then it ends up creating this sparse point cloud. So it understands the intrinsics of the camera and the cameras itself based off of these interest points in the three-dimensional space. After that, we end up going ahead and taking that information, recalculating again, creating dense point clouds. And this is why, if you've ever seen any either photogrammetry or any other systems where they're like, oh, and this is a point cloud, this is what they're normally talking about, is something that actually resembles or looks like the final mesh before it actually gets created. After that, you end up filling in the blanks, a little bit of understanding based on the intrinsics of the camera, different depth information that you've gone ahead and created, and then you end up getting a full three-dimensional mesh out of it. And the big thing, and this is what a lot of people spend most of their time on, is optimization. So, like what we have per frame ends up being about a gig per one single videogrammetry frame. And obviously, you know, you can't really play that back on absolutely anything. So we send it through a massive cleanup process, and one of the really cool things that we've done recently is called temporal preservation, or at least I call that because I invented it, so I can. So it's the capability of being able to save the mesh's information over time. So you have frame 1, frame 2, frame 5, frame 50, it doesn't really matter. It ends up saving not only the texture information, but the intrinsics of the information that comes from the mesh itself. Its parameterization and how it's actually sliced, so that you can go ahead and clean up and optimize to a massive difference. So to give you an idea, if you do just regular chunking and you really get down, most people are at about 20 megs a second. The temporal preservation that we're utilizing gets us down to about 1.7 megs a second. So it's a really awesome optimization process, but nevertheless, it takes a lot of time, a lot of energy, and a lot of thought. All right, that's that. Okay, so photogrammetry in general is super awesome technology, and there's a whole bunch of different ways that you can go about doing it. You can go single camera, which is literally someone just standing there and taking a bunch of photos of different space. Like if I was going to take photos of this stand here, I would just stand and go ahead and make sure that I have all the different places, so that when it goes in, generates the mesh, that we have everything that we want. You can also do a multi-camera rig, and this is where you start getting to more advanced things, and especially when you're trying to deal with a person or a moving object. People, you know, if you start to breathe, it can actually affect the entire clean setup and the photogrammetry output. So taking a giant array, which you can see on ones like on the top right, which, oh, I have a laser. Ones like that, where you can go ahead and go through and take photos of the different setup. So the next one that we're going to talk about is a videogrammetry rig. And so these are a little bit different in the idea that photogrammetry, I just take a still, and now I have a single point in time. Videogrammetry takes that and launches it up a notch. And the idea is that you have to do this over time, every single frame. So if you're doing 30 frames per second, and one of our rigs is 104 cameras, I have to have 104 cameras sync on the same exact time. It's a lot of fun. But this is one of our smaller rigs. This is actually a 24 camera rig. And then we didn't end up putting in the 104, but we have some really cool images. If you end up going either on our website or on our YouTube channel, you can see video of us recording with that. It's really fun, really interesting. The next one ends up being multi-camera photogrammetry with videogrammetry capabilities. So you can do multi-camera photogrammetry just as it stands, and then you can bump it up a notch. So we have some clients that are photogrammetry experts. Like, this is all they do. They go out there on 18-wheeler trucks, and they go out in the middle of Georgia, because that's a big place right now for scanning people. They go out into the movie sets, and then they set up, and somebody, you know, big name star comes out, boom, take photo. And then you can be able to take those same rigs, and then you can scale them up, so long as you're able to set the timing. And that's a big thing. The other thing that you can do with photogrammetry, and this is a really cool thing, and some people may have seen this, is aerial. So a lot of different things. You've seen Google Maps. They have an aerial version that utilizes photogrammetry using satellite data, different things like that. So, okay. So what do photogrammetry point clouds do? So we talked about the difference between sparse point clouds and dense point clouds. How do you get from point A to B normally? And then how do you go ahead and create that and turn it into something? So one of the big things that is a difference between multiple styles is if you have just standard cameras, or you can utilize infrared cameras as well. So in this slide, we're talking about the difference between a sparse point cloud, which comes from a camera. So you have to go ahead and understand the intrinsics of the camera, where it is around three-dimensional space. Out of that, you end up creating a depth map. And how many people have dealt with depth maps before? We got a bunch of people from from CG World right over there. And so, depth information, just a white and black image that tells how far away an object is based on that camera's view. And then out of that, we end up creating a dense point cloud. So you have all these depth images that you create out of that, and then based off of all the images, then it goes ahead and combines it together in creation of a single mesh. The next one is IR cameras, and this is the reason why a lot of companies are currently using infrared for their technology, is that they are able to get the depth information directly out of whatever they're recording from. There's positives and negatives on each one of these. The thing that we believe in is actually just standard photogrammetry, and the reason why is data sets at this point in time and the way that we understand them is continuing to evolve. When you have depth information, you're only pulling depth information to understand how far away objects are, and you don't have enough cameras to understand and create depth information from your camera array. As we get better in understanding, and this massive advancement, especially in this last year, as it comes to understanding images, three-dimensional, and just advanced machine learning, in the future we'll be able to do a massive amount with those. If anybody's paid attention to NVIDIA and what they've done with their advanced machine learning, being able to understand that an image is blurry, out of focus, has bloom in it, motion blur, and is grainy without any training data in the next several years, it's just going to be child's play to be able to understand the original data set so long as you have enough information from your photos. Okay, so what is volumetric capture? So we understand photogrammetry. Let's move on to volumetric capture, which is videogrammetry as well, depending on who you ask. So volumetric video is a video technique that captures three-dimensional space, such as a location or performance. This type of videogrammetry requires data that can be viewed on flat screens and also can be done on 3D screens or VR goggles. Basically, the breakdown on that is you can view this anywhere. It's supplanting what is video. And so the next move for video is going to be able to just add depth information to your two-dimensional space. Think about being able to go into Friends, or some other major television show, and you're in the experience, whatever your favorite Netflix show is. And then you can walk around and be with them. Or you can be in any part of a movie. As well, since you're capturing people in three-dimensional space, think about how much this could be added to movies. So if you're a movie director and you go, I really like that shot, but can we turn it down? Angle it just a little bit, about 5 degrees. You can do that safely, effectively. And since it is a three-dimensional mesh, if you're doing anything with post, or if you're doing anything with physics-based systems, like an explosion or something like that, you actually have the three-dimensional object that's already there. So super cool. Okay, so different types of volumetric capture. You have structured light, infrared, LiDAR, and of course, photos. So the really cool thing with structured light, if anybody hasn't played with structured light, is that you end up taking a camera, and that one right there is actually named Structure, and it's from Occipital. And what it does is it goes ahead and it shoots out a blast of light, and you can see here's their light emitters right there that shoot out at half the intensity of the sun for a very short amount of time, and it actually shoots out a pattern. And based off of the amount of time that the pattern takes to bounce back, and how much that pattern is perturbed on the surface, they know how far away objects are. Clever trick. The next one is infrared. Infrared technology can be structured, so it can use that same grid style pattern, or it can just be a beam. And so you have these wide beams of infrared, or you can have a multi-infrared array that can be captured in multiple locations, and they can use things like time of flight to go ahead and get information back. If anybody's played with the Kinect, the first version was mostly time of flight, and the second one has a lot more advancements, and the newest one is what we're all excited for. And so keep your eye out for that. LiDAR. LiDAR is actually a super cool style of technique, and you can go ahead and bounce that off of planes, and you end up seeing that for things like large areas. The fidelity is really amazing, and if there is enough bandwidth to it. A lot of the stuff that you see for like self-driving cars has that same style of LiDAR, but they tend to use a cheaper version that's a three-dimensional puck and stuff. Or spinning puck. So comparing different photogrammetry types, and we'll go, this is, it's a cost comparison versus computational needs. Single camera photogrammetry ends up being obviously fairly cheap. You have a camera, you walk around an object, take photos, scan it, push. And then the next one is single IR capture. Obviously, the costs are a little bit more, but since you actually have your depth information once it comes out, you're good to go. The computational needs drop. You can actually jump past the creation of your depth information, and you're into a mesh, and you're good to go. The next one, obviously, is a multi-camera photogrammetry rig. Now you're starting to get into some, big toys. You end up having just the stands alone for one of our rigs, and we're talking about, one of our cheaper rigs that we have ends up being, $500 to $700 just for stands. And then some of the more expensive rigs that are out there, if you look at like Intel's rig, they spend multiple millions of dollars just on scaffolding. And then of course you have the cameras that go along with that. If you think about, even if it was a $50 camera, you have 104 cameras. It gets expensive very quickly. The next one's a videogrammetry rig. Same exact idea. Cost may or may not go up. Most of the time it doesn't. But the big thing that you have is computational needs. So you're not doing it one time, you're doing it for every single frame. And that just massively goes up. And then the very last one is IR volumetric with cameras. And of course, your costs end up going up because the infrared technology and being able to use those style of cameras end up being a little bit more expensive. But the computational needs go down, as we spoke about, the same with just single IR because you already have that depth information. Okay, so use cases. We've talked about this a little bit. Things like entertainment, object preservation. This is a really cool one. Now think about several years ago in Egypt there was actually an uprising, and there were issues with some of the antiquities that got damaged. And so, through history we've actually lost antiquities, not only, through massive amount of history, but within our lifetime, within the last 6-7 years, there's been so many of those. So if you could do things like scan these objects and then place them away somewhere safe, somewhere where they couldn't be damaged. We could do a thing, and this is what I call the white box or the white room museum. Think about being able to come in VR, and I'm standing here, and I go, okay, I want to go to the Louvre. I want to go to the Metropolitan. I want to go to all these different museums. And these things are safe. They're taken care of, and we never have to worry about them for the future because they're going to be somewhere that people can't damage them. I mean, even a little while ago, there was a kid who just tripped, ripped through a multi-million-dollar painting. It's things that happen. We're humans, we make mistakes. How do we save these things? Another one's crime scene investigation. Think about taking photos of a crime scene. I mean, it could be out there on the road, or it could be someone's house, or things get damaged. You end up losing information. This allows investigators as well to think about things the way that they think about things. I don't know about you, I don't live in a two-dimensional environment where I look at photos and go, okay, this is 15 feet away, and that's 20 feet away, and how far away were they at? At this point in time, then you could go ahead and scan the entire room, and you can walk from one side to the other. You can get a real understanding, and then be able to use that in actual, in juries, so that they could actually understand what's going on as well. Being able to take them to an actual location, and then it's not where they could possibly damage it. So that's always cool. Medicine, so this is a really interesting use case, and we do a little bit of that with scanning technology, but one cool push would be to be able to help someone either understanding a degradation of a facility of some sort. If you have somebody with Alzheimer's, being able to see how they've progressed, and then be able to take that information as well. If you think about telepresence or telemedicine, you have something like a contusion or a bump. Those things don't actually show up very well on just regular 2D images. You know, people are trying to show what's going on. And then as the technology gets cheaper, obviously this can be something that's in everyone's home, so that when they're doing telemedicine or telepresence through that, they can actually see what's going on, get better diagnosis. In sports, has anybody seen what Intel's doing? Wow. Nobody plays sports. Nobody. Okay. So I don't either, but you know, obviously this is my world, so I got to know. And so they've gone ahead and they've set up a myriad of different football stadiums, and then they go in and they have these really nice cameras that line the edges, and they're taking people through plays. So they're scanning, hit a single frame, and then people at home can go, "What was that hit like? What was that pass like?" And you could literally be, you know, some major quarterback and then they send you through, or you can move around however you want and just see what it's like to be on the field. Just super awesome use of technology. Okay, so we have 4 minutes and 10 seconds. And so I'm going to try to explain to everybody what's the difference between VR, AR, and MR. We can do this. I believe in myself. Okay, so VR, completely digital. You are the environment is you, you're in it. MR, other side of it. The world and the environment are intertwined. At some point in time, once we really start to understand, we really get good at making environments and making immersion, then people are going to question what is reality, what's not reality, and where do things end. Very cool. And then AR, I tend to think about it, and we're getting better at how we're doing it, as a sticker on top of the world. It's great for information. It's great for training and being able to sit there and go, hey, this is, you know, I'm an oil change mechanic, and I want to go ahead and figure out where is the filter. I don't know. I've never seen this car before. It goes, okay, here is the information as an overhead that is as a pair of glasses that's on me. And it goes, okay, go over 5 feet, go up. It's going to be over here, you know, or it's behind the front wheel well. If anybody's seen any of the new fun cars, that's how you have to do it sometimes. And this will speed up how people work. And so I tend to see that as more of a way that we bring information into the world versus you are the world, and then the world is you. So it all brings it all together as one full setup. I love all the technology. Every single one of them has a good use case. Anybody out there who does contract work or works doing this technology, I would recommend just educating people on what's the best. You know, I've been pulled into many a meeting, and our client would go, "Well, we've got to have something new and technological. We gotta push." And I'm like, "Yeah, of course, everybody wants to do that, but we need VR." And I'm like, "Yeah, no, I don't think that's a good use of, you know, technology for you to be able to teach people where this thing is down the street. Wayfinding would be a much better setup using someone's cell phone and augmented reality." So always the best use for the use case, and always remember that technology, when done right, is going to actually help all of us. If every single one of us decided we're just going to go ahead and pick up and just use the technology just because that's the technology, you know, then we end up getting subpar experiences, and then we push people off. I can definitely say it is very difficult for us to get medical clients into VR because of early cardboard projects that came out. And they go, "Oh no, I've seen it before. I've seen it. It's all, you know, it'll make you sick, it'll make everybody, you know, it looks bad, it's horrible." And as much as it burgeoned and it pushed the technology, there were a lot of people in the very beginning that said, "Hey, here's the gold rush, let's go." Always do good, always try to make an amazing experience. So, future technology. I really like LiDAR. I definitely believe that is end up solving a lot of our problems in how we actually scan objects and how we create three-dimensional assets as we go along. Optimization for computer vision and machine learning, we talked a little bit about that, but obviously keep your eyes open. Everybody is trying to burgeon, move this forward, and let's all work together. There's absolutely no reason to hide everything under a rock. If you go to our website, you can see a lot of information about the technology that we're using and what we're doing, so you can see more from us. Further acceleration through multi-purpose built systems, purpose-built systems, I did it backwards. One of the big things that a lot of the technology had been previously is everybody was trying to make these systems that were massive and they only do a single task. A really cool thing that's happening with IoT style systems and what we're utilizing them for is being able to set them up as a record station. So it's really easy for us to go ahead and also iterate upon everything that we're utilizing. In high fidelity systems like Wi-Fi measurement, and this is not a joke, you can actually bounce around Wi-Fi through a single room and see what's inside of it. And there are a lot of companies right now that are trying to put it in police and military. But being able to use that same technology to be able to scan a room means that I could put up 15, 20 really nice cameras up and be able to get the color information, but get the mesh information from bouncing around Wi-Fi waves. So that is the future of technology, and I want to say thank you all very much. You've been an amazing crowd. I see it's continuing to fill out, and I hope you all have an awesome day. And that is my email at the bottom if you have any questions, comments, concerns, or if I flipped around too many words during my reading. All right. Thank you.